Hello everyone. Today I'll be presenting the accepted work on my mobile knows that I'm driving in vehicle relative blind localization of a smartphone. We are a group of researchers from Indian Institute of Technology, Kharagpur, India. Several road accidents are reported regularly across the globe due to the driver's distraction, as it comprises of 20 to 30% of the car collisions on road. The distractions can be of many kinds. Example, continuous honking of the pure vehicle, loud noise in the car, front vehicle activities, etc. But one of the major distraction is the usage of the mobile phone, as it is also stated by US National Highway Traffic Safety Administration, NHTSA, that the usage of smartphones while driving is a very common practice among teenagers, which results in accidents and killings taking place every year. This necessitates preventing the usage of the smartphones while driving. The smartphone can be distracting when it is being used by the driver, whereas it is not distracting when it is being used by the passenger. For this purpose, we have to locate the smartphone, and various existing works are being conducted on computing the location or estimating the location of the smartphone with the help of the Bluetooth, jammers or antennas, the car speakers, the front view of the using the cameras of the mobile phone, etc. However, most of these works mainly leverage on an external specialized hardware to detect the location of the mobile device, and these hardware or devices can be tweaked by the driver by acting as an adversary. For this purpose, we aim to develop an adversary model where the smartphone user always want to use the device irrespective of whether he or she is the driver or the passenger. We have the following contribution to locate whether the driver or a passenger uses the smartphone, to locate blindly without using any external hardware, to leverage the unimodal acoustic signatures inside the running vehicle to locate the smartphone. For this purpose, we collected the data in a very controlled manner. We collected audio data using the microphone of the smartphone at different locations inside the car, at the vehicle, that is the vehicle dashboard, hand or lap of the driver, hand of the passenger sitting at the front, and the hand of the two passengers sitting at the back. The data was collected for the 3 automated geared cars with an interval of different duration, and also was collected for 3 different driving scenarios stated as static, normal, marketplace turns, and human interaction. In this case, we try to develop the blind localization with the following 2 assumptions: that no forward communication from the smartphone of the driver is possible, and also the phone can be kept anywhere inside the car irrespective of the owner's identity. As we can see here, that the acoustic harshness, which is obtained from different sources of noise, that is the wind noise, engine noise, gearbox noise, or the wheel noise, vary across different positions inside the car. As it is seen in this diagram, that the noise power distribution varies across different locations. For this purpose, for extending our research, we try to compute 2 different research questions. One is that, can a smartphone capture rumbles under different acoustic environments? And do these rumbles inhibit different signal characteristics near different seats within a car? For this purpose, we firstly look into the spectral analysis computed from the frequency domain by generating the STFTs from the frequency component of the signal. As it can be seen that at different locations inside the car, the frequency components or the frequency patterns varies. So the frequency components present inside the acoustics will help us to distinguish the location inside the car. Next, we look into the time domain analysis at different locations inside the car and for different surrounding scenarios as stated while data collection. In this scenario, we have observed that for all the scenarios, the signal power is not in a similar, not showing a similar pattern or a distinct properties, because it varies according to the changing noise and with time. So signal power alone is insufficient to localize the smartphone. As we have observed that the frequency components are the distinctive signatures to demarcate whether the smartphone is in the hand of the driver or the passenger. So with the frequency components, we developed our system BLA, which is blind localization using acoustic harshness. We explore 2 features for the development of the system. One is the periodic frequency and another one is the fundamental frequency. The rumbles which are generated from the car's engine or the AC vents may repeat its signature after a certain interval of time, which is defined to be a periodic frequency. And the fundamental frequency is the lowest frequency of the periodic waveform throughout the signal. The fundamental frequency may vary according to the pressure of the airflow. As we can see in the diagrams clearly, for the three different cars, the periodic frequency is highest in case of the driver, as the driver seat is closer to the engine and can hear different continuous steering wheel movement. The fundamental frequency is lowest in case of drivers because the driver seat is often occluding the airflow which is coming to the mobile phone held while driving. So based on these two features, we develop a single step algorithm that can blindly localize a smartphone within a vehicle concerning whether it is being with driver or a passenger. We have the three different localization labels. One is the phone with the driver D, phone with the passenger PF, and phone with the passenger back, that is PB. For this, we splitted the audio signal into windows of length T seconds, and each window was pre-processed for different frequencies of, for a frequency band, which is the general frequency band of a rumbling noise. Based on these two features, we developed two variants of BLA. One is BLA P and another one is BLA F. We evaluated these variants in one of the cases for the driving locations as stated above. We analyzed a micro F1 score, micro precision, and micro recall for the two variants. As it can be seen from the table that in case of BLA P, the micro F1 precision and recall both are exceeding 80% of 80% in all the cars. As from this, we conclude that the ambient mechanical noise are very periodic and thus generate a good performance in case of the periodic frequency. But we also observe a considerable amount of performance in case of BLA F using the fundamental frequency. Next, for the diversity, we computed the location-wise performance at driver location, passenger, and passenger back. For the driver seat, we obtained a higher amount of F1 score as compared to the passenger front and the passenger back. This is because the driver is localized. This concludes that the driver is being localized with the good amount of accuracy. There are confusions sometime in case of the passengers and the driver, and this can be resolved when we combined the two features together. Further, we also compared our work with the baseline, that is by computing the k-means clustering. And our method is by computing the closest similarity using the Manhattan distance between the distinctive features. It is observed that for BLA P, our method outperforms, and the micro F1 is considerably high. But in BLA F, as it is only a single value of the fundamental frequency, there is not a much distinction while making a clustering or finding a similarity. Next, we find the robustness of our model in case of different driving scenarios, and we compared a normal driving scenario with the human interaction driving scenario, and thus find out a considerable amount of drop in case of the periodic frequency, as it consists of variety of ranges. But the fundamental frequency is not observed with a higher drop. So we have to keep in mind that we are further looking towards combining both these features to develop a combination of a system. So this concludes our work that the BLA provides a novel idea to solve an important and exciting problem on road safety, and hence it is able to localize the device within a vehicle and understands who is using it. The proposed system is its first of its kind approach that explored such ambient noise inside the car and for indoor device localization. There are few limitations that we discussed, that as there is a confusion between the driver and the passengers, we can combine multiple acoustic features to localize the device. The audio signal is assisted with a lot of noise, and also it degrades the performance. For this purpose, we are looking forward to incorporate any secondary modality such as acceleration or other IMU sensors that can boost its performance. Next, the poor accuracy is obtained using the surrounding scenarios. So we need to sense the driving environment too. Thank you.